Well, hello folks. Well, this time I'm going to make a bit of a lighter video. Okay. Now, I've had a few comments from people who follow my channel asking me to do some examples of the physics that I cover in the videos, and so one of the things I'm going to do is not just cover the stuff that I cover in the videos, but I'm going to actually do some stuff for physics in general. In other words, put up problems and then the solutions with them, and hopefully people who need to study this can use these solutions, these problems and solutions, in order to get through their exams. And the people who are just interested in physics in general can have a look at a problem and see how it's solved. In the last video, I went through a problem of a helicopter dropping a parcel from 1,000 meters, and to see how long it would take for this parcel to hit the ground. And I guess one of the main things was to demonstrate, well, in that case, that if air resistance has nothing to do with it, in other words, it's negligible, then the mass of the object that's being dropped has nothing to do with how long it takes to hit the ground. And for that reason, anything that you drop will hit the ground at the same time, provided that air resistance doesn't play a part in it. As soon as air resistance is involved in it, then there are other forces at play, and of course they will have an effect on how long it takes for parcels to hit the ground. So let's have a look at the problem that's on the board, and let's try and solve these two that are here. Okay, let's have a look at the first problem. A helicopter drops a package from 300 meters while hovering. So how long will it take to hit the ground? Okay, how long will the package take to hit the ground? And I've added this other question over here. How fast would the package be moving as it hit the ground? So that's two interesting things that we can find out. Number one, how long will it take for the package to hit the ground if you drop it from 300 meters? And the next thing is how fast will it be going when it hits the ground? Okay, well, what I've done here is I've divided this up into four, so we've got a quarter of the way down, half of the way down, 3/4 of the way down, and then all the way down. Okay, now let's have a look over here. S equals ut plus half gt squared. Gt squared. Now, I'm emphasizing that because I was listening to a video just a few days ago, and it had on it this complete and utter idiot berating a teacher because the teacher had the temerity to tell the viewers that Newton's law of universal gravity was F equals g m1 m2 over r squared. Okay, and for that, this complete idiot decided to berate the teacher. Okay, and tell the teacher that he was wrong, and that Newton's law of universal gravity didn't apply, even though it's probably one of the most used of all of Newton's laws. Okay, well, you know something? There's gravity right there. And you notice mass has nothing to do with it. Okay, so we're going to make this calculation using this formula over here. Alright, what have we got? S starting at 75, the initial velocity is 0, because you notice that the helicopter's hovering, so therefore it's not moving horizontally, it's just staying right there where it is. Okay, gravity, that's the gravitational field strength on Earth, 9.8 meters per second squared. Okay, we know this because we can measure it. We can drop things and see how long they take to hit the ground. We can check to see what the acceleration is, so we can see how long it takes at various places before it hits the ground. So we can check to see what the acceleration is. It's not that hard, okay? Not even for a flat earther. Okay. Now, so at 150, we'll do it for 300 first. 300 is 9.8 over 2 times t squared. If we make t the subject, we'll have the square root of 300 over 4.9, and that turns out to be 7.8 seconds. So from the time that it leaves the helicopter to the time it hits the ground will be 7.8 seconds. Now this is the interesting part. If we replace that 300 by 150, we end up with 5.3 seconds. If we replace that 300 by 75, so in other words only a quarter of the way, 3.95 seconds. Almost 4 seconds just to reach a quarter of the way. Then to reach halfway, 5.3 seconds. To reach 3/4 of the way, 6.8 seconds. To reach all the way, 7.8 seconds. So clearly you can see that this is speeding up as it's going down. It's accelerating. Okay. All right, now, next one, we're going to have a look at this second question. How fast was the package moving when it hit the ground? Okay, well, what we'll do is we'll actually look at how fast the package is moving along the way. So when it reaches a quarter of the way, when it reaches halfway, when it reaches 3/4 of the way, and then when it reaches all the way. Okay? Alright, so here is our formula. V equals U plus GT. Notice again, gravity plays a role in this. Okay? Now, let's have a look. So at, we got here, we've got 5.3 seconds. Okay, at 3.9 seconds, the package is moving at 38.22 meters per second. And that means 85.5 miles per hour. Okay, at 5.3 seconds, which is halfway, so it's halfway to the ground now, it's 5.3 seconds, 150 meters, it's going at 51.94 meters per second, which is equivalent to 117 miles per hour in the old language. Now, 3/4 of the way, 225 meters further down, it takes 66.8 seconds to do that, to reach 3/4 of the way, 6.8 seconds. At 6.8 seconds, it's traveling at 66.64 meters per second. And this is 149 miles per hour. And then finally, just as it hits the ground, at 7.8 seconds, it's traveling at 76.44 meters per second, and that's 171 miles per hour in the old language. Okay, how did we reach these figures? There's our formula right there. The velocity, that's this, velocity in seconds, is equal to u being 0 because it started off at rest, 0 plus gt, g being gravity because there's no other reason for it to head to the ground, and t being the time. Okay, so here are our figures for B. Alright, let's have a look at the next question. Okay, let's go over the solution for question 2. So once again, question 2 is the same helicopter, that one over there, is moving at 20 meters per second, and how far will the package fall past the point that it was dropped? So in other words, how far will it from here to here? So that's the point that it's dropped. What is the range that it will fall over the ground? Okay, so let's have a look and see if we can work that out. First of all, we've got two components that we need to consider. First, there is a horizontal component, in other words, going this way, and there is a vertical component going this way. Now, again, you notice that this package still has the momentum that it had when it left the helicopter. The helicopter was going at 20 meters per second. So the package was also traveling at 20 meters per second. So when you drop the package, it's still going at 20 meters per second. Okay, it has not lost its component, its horizontal component. It's still going that fast. Okay, it has still got its momentum. Alright, so has it got its momentum as it's going across? That's 20 meters per second. So U is, that's the initial velocity, is 20 meters per second. Okay, so if we have a look at the horizontal component first, horizontal component, G is equal to 0. There's no gravity horizontally. Okay, gravity only applies down towards the center of Earth's mass. Okay, that's where the gravitational field is. The gravitational field is towards the center of Earth's mass. Okay, so G for the horizontal component is going to be 0. So if you replace 0 here with G, all you've got is S equals UT. So therefore we can go back now and have a look for what is S equals UT, that's the distance, the range for UT for each of these time frames. So for 3.9 seconds, as the thing falls down 75 meters, okay, so by the time it reaches 75 meters, it will have gone 78 meters across. So horizontally it would be 78 meters across in the first 3.9 seconds. After halfway, at 5.3 seconds, again replacing it in here, at 5.3 seconds, as it has fallen 150 meters, it will have displaced 106 meters. The range will be 106 meters further along. Okay, at 3/4, at 6.8 seconds, at 225 meters down, it'll be even further, at 136 meters further along. And then finally, when it hits the ground, at 7.8 seconds, it will have traveled along 156 meters from the point at which it was dropped. Okay, so it's dropped at 156 meters further along. That's where it hits the ground. Okay, so let's have a look at the next part of the question. How long will that take? Well, we've worked it out. It's going to take 7.8 seconds. So you can see, if we put the figures back in here, 7.8 seconds, we get 7.8 seconds. It makes no difference. The vertical component makes no difference. Okay, so it doesn't matter whether this was moving along or whether it was hovering. It still takes the same amount of time to hit the ground, 7.8 seconds It takes 300. It doesn't matter that this had a horizontal component that caused it to move 156 meters further along. Alright, so hopefully you've got something out of this, and you've worked out how we might calculate things like vertical drop, like the time it takes for something to fall from a given height, for the acceleration, and over here where something's moving across, in other words, that already has a horizontal component about the velocity. In other words, it's moving across at 20 meters per second, so it has momentum already. Okay, and because it's got that horizontal velocity that's going on, all right, what effect does that have on the distance, the range, when it hits the ground? And we can see all the way down, we can see how much it would take all the way down. So at 78, at quarter of the way, it would have already gone 70, the range would already be 78 meters across like this. You know, at 3/4 it'll be 136 meters across from there to there, and all the way, by the time it hits the ground, it'll be 156 meters. Okay, but what's important here is realizing this. The main component that we're using here for vertical component is gravity. Okay, so Earth has a gravitational field, and this is what we're using. Anything with mass in this gravitational field will experience the gravitational field. In other words, it will head towards Earth's center of mass. Okay, this is what it looks like to us, regardless of the reason for it happening. This is what does happen. This is what Newton described. Newton described what does happen. Newton explicitly told us that he didn't know why it happened. He just knew what happened. And this was the point that that teacher was making. That fool who berated that teacher didn't understand that concept, and probably still doesn't understand it, and even after watching this, probably still will not understand it even then. Well, mister, it's your problem if you don't understand it. Okay? Alright. So, if you like my videos, please press the subscribe button, okay? And also the like or the dislike button. If you're a floofer and you actually don't like this, or you don't understand it, or couldn't be bothered with it, press the dislike button. Smash it. Go on. I'll wait for you. Go on. Go hit dislike right now. Those of you watching, please press the like button or the dislike button, whatever you like. Okay? And I will do more of these. So what I intend to do is to look at some physics problems and offer their solutions so that you can understand how this works. So I'm not just going to give you the theory behind the physics and describe what happens, but I'm actually going to put up some problems that we go through and solve together. Okay? Alright. I'll see you next time. Press those buttons, please.